Let's solve this problem of problem 56 of your textbooks. It says that a bob of a stationary pendulum is given a short hit to impart a horizontal speed of root 3 g. That means, say this is the pendulum. I have drawn a semicircle already because drawing a freehand circle is very difficult. This is a pendulum and it is given a short fit, say u, initial velocity is equal to L, where L is the length of the string. Find the angle rotated by the string before it becomes slack. Here, a similar problem you will face many places. I want to make it clear to you that a question you may ask, why will it not rotate the full circle? And why it will at all become slack? Investigate a little, you will find there are reasons for that. If U is equal to root 3 GL, then its initial kinetic energy, let's write kinetic energy ZO is half mv square, which is equal to half m3gl, which is equal to 3 by 2 L. Now, initial kinetic energy is 3 by 2 mgl. Now, wherever it goes, it has to go there at the expense of this much energy. It does not have any more energy anywhere. It does because the problem says it does not, in no other push, no other engine, it has got only this much energy. So I have proposed all of you to first check, will it reach the horizontal position? Checking this is very easy. It will not elongate your problem much. Say A. Will it reach A? Look, A is at the height of L. A is at the height of L. And there is a force acting here, which is mg. So what is the, let us write the symbol U, is the potential energy at A equal to mg into L. And what was the initial kinetic energy? 3 by 2 mg. So we find here that potential energy required at A is less than initial kinetic energy. Therefore, we can write, so the bob will reach point A and also cross it, because for to come to A, it needs only mgl. So still half mgl is available. So it will definitely cross. Now let us find out, will it reach point B? Find potential energy required at B is 2 mgl. And we find potential at B, gravitational potential energy at B is more than initial kinetic energy. So we'll not reach B. That means it will reach somewhere here, somewhere up to here, at the point, say, Q, at the point Q, where it will spend all its initial kinetic energy. And that is the point where the string will become slack. We shall further see why the string should become slack. Now, in order to say that, let us consider the tangential velocity at Q is V. Consider tangential velocity at Q is equal to V. And 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 this height from and this height, consider this total height is h. Then the kinetic energy at Q, kinetic energy at Q, I shall write explaining the whole thing to you. Kinetic energy at Q, kinetic energy at Q plus kinetic energy at Q will be equal to kinetic energy at Q will be equal to kinetic energy 0, that means the starting kinetic energy, minus the potential energy at Q. That means kinetic energy at 0, zero kinetic energy or starting kinetic energy will be kinetic energy at Q plus potential energy at Q. Right? From here, we can write kinetic energy at Q is its tangential velocity v, so half mv square. So this kinetic energy is 0. Kinetic energy is 0 is mu square half mu square will be equal to kinetic energy at Q is equal to half mv square plus potential energy at Q is mgh. From here, what do we get? All m gets cancelled. So also if we multiply it by 2, then we get u square is equal to v square plus 2gh. What is h? H is equal to, I put it in the bracket, h is equal to L plus L cos theta. If you consider this whole angle theta, that is the answer that we are trying to find out, then this angle is 180 minus theta, 180 minus theta. This angle, if you consider this angle will be 90 minus theta. So this height will be L cos theta, right? So this is this. Therefore, from here we get v square. So we get v square is equal to minus 2gh is L plus L, h is L plus L cos theta. Okay? This is one equation. This is one finding where we are equating the energies, potential energies and kinetic energy. And this kind of a problem, this kind of pendulum problem, you will always have two equations. One is equating the energy, another is equating the forces. So this is the position of the position of the bob Q. So this, I take this red mark, the force mg works in this direction. Force mg works in this direction. So the radial component of this force is mg cos theta. Now look, this mg cos theta has to provide the centripetal force required for moving in the circle. This is very important that you must remember. One equation is here we get by resolving the energies. Another equation is here by resolving the centripetal force and the force which provides centripetal force. Now, the centripetal force here, centripetal, if v is the tangential velocity, then centripetal force, I write centripetal force is equal to mv square by radius of rotation, which is equal to L. Who provides this force? This force is provided by mg cos theta. Mg force is provided by mg cos theta. So here also m gets cancelled. So from there we get v square equal to gl cos theta. gl cos theta. We will always have these two equations in a pendulum graph. One is the centripetal force equation, another is the energy equation. So from now we put the value of v square in equation A. Put value of v square from get equation A was v square was on the left hand side, which is equal to gl cos theta. Therefore, gl cos theta is equal to u square. What is u square? U square already we know. U is equal to root 3L. So u square is equal to 3GL. U square is equal to 3GL. U square is 3GL. U square is 3GL minus, this is 2GL. Now this minus and plus becomes minus again, which is equal to 2GL cos theta. GL cos theta. From here we find, all right, let me write it here, or we can do it here. GL cos theta plus 2GL cos theta. In fact, all GLs gets cancelled. GL, 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 all GLs gets cancelled. So now I have cos theta plus 2 cos theta is equal to 3 cos theta is equal to 3 minus 2 is equal to 1. From here we get theta is equal to 1 by 3. Now, find it. Look at this. Theta is more than 90 and less than 180. So, this is the magnitude of cos theta, but algebraic sign of the cos theta will be negative. So, we write here, therefore, cos theta is equal to minus 1 by 3 since theta is more than 90 degree as well as theta is less than 180. This is the second quadrant. You know, in second quadrant, cos theta is negative. Therefore, the answer is theta is equal to cos inverse minus 1 by 3. Answer we have got. But I want to explain something. I want to explain you something so that you can handle similar problems later on. As theta, mind it, as theta increases, let us draw the diagram here once again. This is Bob, this is the Bob, and this was theta, 90 minus 2, 90 cos theta. And if the Bob starts moving further, then what happens? Here, at this point, this is mg, and this is one component, this is another component. This is mg cos theta. This is mg cos theta, which provides the centripetal force. Now, suppose the Bob comes here, then what happens? Mg, magnitude of mg is same. And now look at this. The value of cos theta, value of mg cos theta is no more equal to the centripetal force. That means the balancing between the mg cos theta and centripetal force is lost. So the string becomes slack. As theta increases, if say the theta was here only and this was mg, then the radial component of mg cos theta was much slow. As theta increases, radial component increases. When theta increases here, radial component further increases. So the mg cos theta will become more than the centripetal force required. And if the centripetal force required, say, 10 Newton, but the force which is coming is 12 Newton, then definitely the string will become slack like this. So this is the solution of the problem. We shall take the next problem after a few minutes.